Okay, it should record now. So
Yeah.
I want to talk about my work, which I done this year. And maybe you remember last time when I speak on theory, I spoke about conference in Edinburgh and about one particular talk there. And the talk was about covariant expansion of general relativity. I was quite interested in this topic, so I try to do the very similar stuff, but with another splitting of the metric, and the splitting is the splitting of the metric which is used in non-relativistic string theory when they try to non-relativistic string theory based on Newton-Cartan geometry. And it is quite surprising that I got very nice results, and I want to show them to you. And so my goal is to expand Hilbert-Einstein action, which is fully relativistic action, to the non-relativistic case. And the non-relativistic case means that speed of light is going to be infinity. And there is some problems. Speed of the light is here, for example, but also Ricci scalar is also some function of C. And it is quite complicated to get through this dependence, because it's quite complicated object when it's written in metric, and you need some very careful progress to get the right non-relativistic, let's say non-relativistic Ricci scalar. So I was lucky that during my work, there was another paper about this topic. The paper was written by Neil Obers and his group, and there was quite nice way how they proceed with the one of the splitting of the metric. So it turns out that I try to generalize the results. I will see you there then when generalizing. So so we need some clever way how to make this expansion. So first, I will write the speed of light like some constant with dimension, and then there will be some arbitrary parameter sigma, which in the end of the calculations will go to 0. So C with head is the dimensionful parameter which has dimension of speed and sigma is some parameter. So this make whole work much easier, because I don't need to think about dimensions, because sigma is dimensionless. The square root of here is because I just work with expansion with even powers of speed of light. So my sigma will be have integer powers whole time. Okay, this is sigma, and all fields which I consider here. There are some space-time fields, so this depends on a point in space-time and then on the parameter sigma. And I is some indices. It can be Lagrangian indices or Filbine indices or another type of indices. And every field which I will work will be analytical in this parameter sigma. This means that it has expansion like this. Okay, you can think about, okay, my field will be, for example, metric. So metric have two indices, Lorentzian. So I is now two indices, and it has some expansion. So the first guy here will be, let's say, time, uh, temporal metric, and another guy will be spatial metric, and another corrections. I will be more precise later. And another thing, not all fields can start with sigma 0, sigma to the power of 0. So if the field has some factor of sigma, like 1 over sigma and so on, we just multiply and redefine the field to start its expansion with sigma to the power of 0, just to make things much simpler. Okay, this is just preliminary, just general properties of my expansion, and now how it really looks like. So I'm start with relativistic Filbine. Okay, this E is just Filbine. So we can decompose the metric to two, okay, or it is something like square root of the metric. So we can rewrite metric in this is Lorentzian indices, and capital indices are so-called tangent indices. It's indices in tangent bundle, I think. And I take for my Filbine that it has expansion to something which I call then, sorry, here is small a. Okay, this is something where I'm splitting my fill binds into two fill binds. One is called, or I called it temporal. And the second is spatial. This is temporal in these primes, and in fact, it knows not just time, but it has also some space-time or space direction there, because this index A and A prime, I want them to go to, or I want to index them to go just to some not fixed number, but some number n, which for which I get different physics. I will explain it. If oops. For
Patrik,
yeah,
can you please remind me what is eta?
Eta is Minkowski metric.
Okay.
It is matrix -1, 1, 1.
Okay. Thanks.
Okay, for n equal 0, this is the case which was studied in a paper written by Obers and company. And in this case, you split this fill bind really into the temporal and spatial part. And after all the process, in the end, you should get Lagrangian for Newtonian gravity. The case n equal to 1 means that this is two-dimensional matrix in fill bind indices. And this case is used in non-relativistic string theory. Eric Bershev has a lot of papers where he used this expansion. And for example, n equal to 2, I used this, and my supervisor used it, this splitting in our paper about some brains in M theory. So this is a general splitting of the fill bind, and I was curious what I get if I don't fix this n and I keep just another parameter of the expansion. So this is the starting point. I can define inverse fill bind quite similarly. It is fill bind which has index in opposite way. It starts with square root of sigma, and then there are again some spatial inverse fill bind and temporal inverse fill bind. And from the orthogonal property of relativistic fill binds, this means that for each type of index, these two guys are inverse of each others. So when we multiply relativistic Filbine through the Filbine index, we get Kronecker delta in space-time indices, and when we multiply it through the space-time indices, we get Kronecker delta in Filbine indices.
Another question.
Yeah.
This is not so easy to do. You have to find a t and an epsilon, which are inverses to the t and epsilon before, and they are not square matrices, right? They are
not inverses, and there are some, let's say, projective inverses.
Yeah, but you need a delta in the end.
Yeah, I get delta in both cases. I can find if I have these two guys and I want to them satisfy, or I want to find these two guys which satisfy these two conditions, I can find these two guys.
Yeah.
Okay.
Okay. One more remark, which is quite important. These fields are fields which depends on a sigma. They are not. They have expansion in sigma. They are analytic in sigma. This is the. This is why I multiply this with this factor, and it is to get out the dependence of inverse power of sigma from them. And after, I will make expansion of this parameter of these Filbines to physical things. And this is because it will be messed if I directly start with expansion of these guys. So if I plug these two ansatz into these conditions, I can find some completeness relations which these Filbines and temporal or spatial and temporal Filbines and inverse Filbines should satisfy. One of them is this one. And here we see that they are not in fact inverse. There is something which you must subtract from their contraction to get a Kronecker delta. But they are orthogonal. So this is true. And in fact, they are in the subspaces, they are true inverse. So by this, I mean that when I sum them up with respect to Lorentzian indices, I get the Kronecker delta on subspace of the tangent space. And the same is true for these spatial Filbines. So this is the relation why the things and the stuff behind all what I will say is quite interesting. Okay, I will, for my calculation, I will use these temporal fill binds, and to make it, I don't need to use spatial fill binds, but I will more likely to use the combination of the spatial fill binds, which looks like this. This is something which I will call spatial metric. Okay, so the point here is to expand fill binds, expand inverse fill bind, and found the completion relation between them, where we don't fix the number of the direction in which we scale with speed of light, or with some parameter which will go to infinity, to 0 or infinity in the end of the calculations. So when we have a metric, we can make the same expansion for the Christoffel symbol. So we expand Christoffel symbol to part not EC 0 wrong U. Like this. And I want to say again, these T's are again functions of speed of light, or the parameter sigma and the space time directions. Again, I will make expansion even of these C's, but to keep things quite easy and not so confused, I choose.
Should there not be a sigma in the last?
Yeah,
C?
yeah, thank you. Yeah.
Is that a row, the upper index?
Row,
Right.
all are rows. And
So if you have written the sigmas explicitly, why would the C coefficients -2, 0, and 2, that do not depend on sigma? Is that correct?
no, or all these.
They would still depend on.
Yeah, they still
They depend on sigma, but then it seems like there is a ambiguity where you put the different things.
Yeah. Yeah, in fact, okay, I know. This expansion about these sigmas is given by these sigmas. because
Okay.
when you have let's say full metric, full relativistic metric, it will start with 1 over sigma, and when
I
you
see.
yeah.
So you're trying to explain 3 formulas in one step.
Yeah.
In one go.
Yeah, I can. Okay, when I plug the relativistic metric there, and make expansion, for example, the C minus 2 rho mu will be ugly. Something like that. For this, I just plug the expansion of the field bind to definition of Christopher in the symbols, and I get the prescription for, this is very ugly, prescription for C in the terms of my spatial field bind and temporal field bind. And the point why this expansion is clever and or smart is that I here in one part of this C0 can be used to be a new connection for the non-relativistic gravity. I can, moreover, I can separate this C0 into 2 parts. Quite arbitrary. And if this C rho mu looks like this, TA rho d mu t mu a plus 1/2 pi rho lambda d mu pi lambda nu okay. If I choose separation or splitting of C0 into one part, which I call C, and the second is the rest, it can be easily calculated. Then the C transforms with respect to general coordinate transformation like a connection. And this S transform as a tensor.
Mm-hmm.
And I can use this C as a connection for my theory or my work. And it's quite interesting that if I take this C as the connection, then it is true that the covariant derivative of the temporal field bind is 0, and the covariant derivative of the inverse spatial field line is, or spatial metric is also 0. And this is a structure which is well known, or which is used in Newton-Cartan gravity. And the covariant derivative acts just on the space-time indices in the way how it is normal in general relativity. So when we have upper index, then there is a plus sign. And when we have a lower index, there is a minus. And it doesn't act on field line indices. It just, it's not spin derivative, is covariant derivative.
Is it torsion free?
No, it is not torsion free. It is easy to see. These pi are symmetric. So when we want to calculate torsion, we can see that these subtract each other as same here, but this guy will not disappear, and the torsion of this connection, so some torsion. Mostly I will use this notation for torsion. So torsion is this tensor. So it it's not torsion free connection.
Patrik?
Mm-hmm.
Just to be sure, those two things are different, right?
Yeah, these are different. In fact, I will there be another t. So this, let's call this the like with cursive, something like this. Okay, this is very nice, and unfortunately, it's not true that, because we have here Philbine version of the temporal metric, and here is spatial metric, but it is not true that when we try to differentiate it, spatial Philbine, that's mean, oh sorry, let's mean this. This guy is not 0. So because of this relation, I more likely to use these two objects, like one Philbine object and the second metric object, or like metric object, not two Philbine objects, because the calculations then is nicer. Okay, So we have connection for our theory of gravity. And the same story is for the Ricci tensor. So again, we can expand our Ricci tensor in the power of sigma in the same way as for the connection previously. There will be some R0, and it ends with sigma squared. Again, these powers of sigma are due to powers of sigma in the expansion of Filbine, and these are again functions of sigma and spacetime's coordinates.
Should probably be +4 in the last one, right? The power.
Yes, +4. Thank you. Okay. The only one which I will write here is the most easiest one. And for example, r to the power of -4 which it looks like this thing, and it is the easiest one. Okay, why there is tau? Okay, so sorry. This will be better. Okay, and this combination. So here is pi with indices, and there sum up one with here and second with the second. And here should be sigma mu. So the three indices are these two, but there are sum up with these antisymmetric combinations due to Filbine indices. And if I define something similar to this spatiometric for the temporal Filbine, it will be much more prettier example or result, but still it is one line result, so which is quite beautiful because most of my result was one page results. Okay, so the same can be done for the another powers of the sigma here, but I want to get a Lagrangian, so I need to do one more step. I need to contract this Ricci tensor with a trick to get Ricci scalar. Oh, okay. Again, tau. So there should be something like something which looks like spatial metric, but with the temporal things. And this will contract. Which the expansion of the Ricci tensor, and so on. And finally, okay, this again will be expansion of the Ricci scalar. It will start with r to the power or -4 with factor of 1 over sigma squared. It will be by this guy times this guy, and it will be it will end with r to the power r6 sigma to the power of 3, which will be given by this guy times the last from here. Okay, so now the calculation was very long, but the results are very beautiful. So first, r to the power of, or the part which has sigma squared, this is really 0. Second part, looks like this. Should be alpha, this thing, and C. So still, it could be some awful, but still it has very nice structure. The R0 is still some quite easy. And in fact, we will see that it is very, very beautiful. So here is some total derivative of some tensor, where this is torsion and this is spatial inverse metric. Now there is a guy which is expected there. Here is this is the Ricci tensor for connection C. Okay, so this is something which I don't calculate here, didn't calculate here. I will calculate this later. And the last part of this R0 guy looks like this. There are again some antisymmetric derivative of temporal filbine. And then, okay,
Can I ask?
yeah,
So in one place you write C antisymmetrized for the torsion, but I thought the torsion was essentially
oh,
the antisymmetric derivative of T. So why don't you call the antisymmetric derivatives of T also torsion?
no, torsion is antisymmetric derivative of T, but times T
Yeah.
arrow and
Yeah.
contracted by these indices.
Yeah.
And
So you can just put in a T inverse there and have torsion, and then you would have some free factors of T.
where do you?
Right? You could put in a TA mu or TA alpha, T alpha B.
I think the T is not invertible, right?
Well, in one index it is.
But it is
It's
In the
not.
mu,
It's not a
in-
square matrix.
in the mu index it's invertible. In the A index it's not invertible.
it's invertible in new index.
So you can put that in, couldn't you?
You mean, yeah. You mean here,
For
but
instance.
there are, okay, I can, oh, okay. Something like this, and I can put here TT, and then there is torsion. That's right?
No, the indices, the delta has an A and a B on it, not a mu and a beta.
Yeah. Oh,
Right, so take the contraction of
index.
A, yeah.
Yeah, it's possible.
So, I mean, it seems like if you want to write things in terms of geometric nice objects, it would seem to make sense to write things in terms of the torsion explicitly.
Yeah. Thank you. So there will be something. Yeah, it could be possible.
Mhm.
Yeah, thank
Good.
you. Okay, so I will continue. Okay, something which this guy, this R0 can be also rewrite with respect to the torsion. And here will be something which I called capital tau or curvy tau or curvy t, and this is just this combination. T lambda B. So it's analog to the spatial. Spatial metric. And here are quite different combination of these. Okay. So here it's quite nice that the structure of the temporal field line is important, because one summation is this. So the result will be twice, or the power squared of the torsion, because each contraction is a torsion. But here A sums up with this A, but the torsion will be contracted. Okay, so they are different, in fact. And R2 is something which is not nice, but the R4 and R6 are both again 0. So it could be quite surprising that a lot of stuff is 0 and some stuff is nice. And more surprising is that when we try to construct an action with the use of this Ricci scalar, because we can integrate this piece of the R0, because it's total derivative. And when the total derivative of some vector field, it's integrate over the whole space, it's proportional, it's equal to this thing, which is non-zero just for non-torsion-free connections. So because I have non-torsion-free connection, this, when I integrate this in action, this piece will not be 0, but there will be some part which will be proportion to the torsion. And
in other words, it's torsion full.
Torsion full. Thank you. And after I will perform this integration, the part of the action which we built up with the R0 d pi. There is the Ricci tensor for connection. And then there is this stuff. In fact, after integration, there is some subtraction. Okay. So this is action, which I get from the integration bar part of the integration of the R0 Ricci tensor. And we can see that here is now minus. In R0, there was plus. So this guy, after integration, gives me minus some times this. And this is very nice because when we take our splitting of the field lines that n is equal to 0, this should give us Newtonian gravity. So we can effectively forget about all field line indices. So in this case, this whole bracket is 0. So the part of the action for n equal to 0 is just this thing. And for me, it was totally surprising. Because why there is nothing? But really, this was one of the first results when I started to think that it is not a nonsense. Okay, and I will need also the this R2 part, but it's not. I will not write it here. Okay, so the first big results are these Ricci tensors, and then actions, which I constructed in Einstein-Hilbert way. So all fields here, this mean this pi, this r, this tau, or these t's are still, they still have they still depend on the powers of sigma. So now I make an expansion of these field lines. So this is the point when I expand my field lines to the power of sigma. And similarly, something, something, something. Now this is this for this zero order. There is the same completion relation like for the big ones, relativistic ones. And I don't know how to say it. This is the usual field binds which are used in Newton-Carter geometry. And this is, if you remember my last talk, this is the expansion about which I was talked last time. And the pi is also expansion like this. And these fields are important for me now. Okay. So in Einstein-Hilbert action, I will write it one more times. For some D. I know this guy, and I know that it starts with power 1 over sigma squared. I know that the first is this and the second is first non-zero is this. So this start with 1 over sigma. The big question is how the volume element scale with respect to sigmas. And it scales like sigma to the power minus n over 2. So my goal now is to give good Lagrangian, which can describe a non-relativistic gravity. So I will do it in the very similar sense like the previous expansions. Again, Okay, first I need to get rid of some explicit expansion of the speed of light. By explicit expansion, I mean the expansion of the dependence. Here, this has some biggest power of the speed of light, and so here. Okay. So if I want to work with Lagrangian, which is analytical in sigma to make expansion in this sigma. So I need to redefine new Lagrangian with bar, which will be analytic in sigma. That's mean that there will be some Lagrangian without power of sigma, right? Lagrangian with first power of sigma and Lagrangian with second power of sigma. I hope that I call this Lagrangian.
Oh, okay.
Like this. So this will be Lagrangian of leading order. This will be Lagrangian of next to leading order. And the last one will be Lagrangian of next to next leading order. I hope that this is right. Okay, we will see. Yeah. This should be right. And first, I need to redefine my Lagrangian. So I need to multiply it with the right power of sigma, and the right power of sigma will be something like this times 1 over sigma squared, 1 over sigma, but it doesn't matter. And then I get this expansion of the redefinite Lagrangian by just Taylor expansion of the, okay, so this guy will, it will start with sigma 0. And just for multiplying, and then,
Can I ask a question?
of course,
So you said that it starts with sigma 0, and I wanted to ask, does that depend on how big n is?
yes, it's but it's given by the volume element. There is only dependence on the n.
I guess
Yeah,
the
but
answer
this-
to I think the answer to Stanislav's question is that you probably put a factor of sigma outside your definition of L
Yeah.
bar.
Okay. So is it still possible that the whole thing would have some 1 over sigma terms, or?
Say it again.
Well, if I understand it correctly, depending on the n, how big it is, you could get some 1 over sigma terms, so sigma with the minus power. So is that like a restriction for n? If you don't want that n has to be bigger or lesser than something?
Okay.
Do you always redefine it in such a way that you will start with sigma
I
0?
think when I denote, let's say, this thing like, okay, it's SH. Oh. This will be the best. So the Lagrangian for this Einstein-Hilbert action should be 1/sigma to the my new Lagrangian.
Yes.
So
Okay.
when it's n0 and it's okay, and n cannot be negative. So it should doesn't give me anything new. But
Yeah, okay. Thanks.
okay, so I have this guy, which is analytical in sigma, and now I can make usual Taylor expansion of this. And the last one. And so on. So, but the problem is that the dot here is not just a derivative, but there is, because my fields are depends on sigma, also depends on sigma. The same as here, and also there should be contraction between the space-time and field by indices. So I'm interested in these three Lagrangians, and in fact, I'm most interested in the quadratic one, because it should be in the case n equal to 0. This Lagrangian should give us Lagrangian for Newtonian gravity. So I expect that for another case, n equal to 1 and n equal to another number, it could give us some generation, general version of non-relativistic gravities, which could be interesting for people who works in or who try to make some non-relativistic string theory or so on. So I'm most interested in this guy. So after this Taylor expansion,
Why do you have sigma equals 0 on the left-hand side?
here,
On the left-hand side.
here. Yeah. This should be more likely sigma 0 is equal to 0. If you know what I mean.
Oh, okay. Maybe you are distinguishing between implicit and explicit
Yeah,
sigma dependence.
it's I make Taylor expansion of some function around a point. So I make Taylor expansion of this function of the sigma around point sigma is equal to 0.
Right.
So then there should be, in the second term, there should be sigma minus sigma 0, probably. Something like
Yeah,
that.
but
Yeah,
sigma 0
yeah,
is
but
0.
sigma 0 is 0.
Oh. Okay.
So the guy next to next leading order is quite complex. So I will try to write nice. So there is just second derivative of Lagrangian with bar. And in fact, this is just a part which comes from R, I think, 2. This is just when I rewrite R2, which is quite ugly, it will be here. Then there are part where here is a third field in expansion. So for me, that's mean that, for example, for in expansion of field by T, there is field B mu, and so on for this P. So there is B mu times, and this is just equation of motion for Lagrangian of leading order. And And there is this, where this is equation of motion for Lagrangian next to the leading order, and contracted with fields in the second, or in the fields which are second in expansion of the field line. So for field line T, there is the field M, and the last part there. It's in fact is second variation of Lagrangian leading order Lagrangian. And so on. And it turns out that this bracket has this is H, the field, the first field in expansion of the relative ice. This means spatial metric. Okay, I will say what's F's are. Okay, FRs, F looks like this. Okay, there is plus something which I again should define, but it should, for case n equal to 0, be a field strength of some U1 connection. I still don't get it much, but this is the first part, which is non-zero, but the all other guys in this bracket could be written as this this combination times some tensor. X is some tensor which has a very difficult, very hard or very long, I don't know how to say it. It's not nice, but in every terms, except this one is this combination. And what is nice is that this thing if I, okay, I can have the equation of motion for leading order Lagrangian. It gives me equations of motion for this. And this equation of motions can be satisfied by just this condition.
Can I ask?
Yeah,
Why do you call it a U1 connection?
I don't call it U1 connection.
Oh, you said so.
For the case n equal to 0,
For case n equals 0, okay.
they called it U1 connection in the paper.
Yeah, there's only one index.
Then there is only one index.
Yeah.
Yeah.
Yeah. What is the symbol in front of the two H's in the red circle?
E.
And
Okay.
what is it?
Yeah. E is volume element, and it's, you know, my G has scaling of sigma n over 2. So when I define capital E like this, then small e is capital E when I take sigma equal to 0. So it's non-relativistic volume element. Okay, so what I want to say that my goal is to obtain this Lagrangian. I have all this stuff calculated. I should check that. And I also work now on how to simplify this Lagrangian with use of when I use that this condition holds. Because Lagrangian, this is something which is off shell. It should be true everywhere. But I get it. It's very, very, very difficult. It's one page expression, and I want to simplify it. And it looks like that if I can somehow incorporate this condition, this off-shell condition, which comes from equation of motion for another Lagrangian, it will be much more easier. So the main result is this thing. I already have it, and this is something what I'm thinking about now to simplify this awfulness. And in fact, I don't write it anywhere in the one piece. I have each piece separately in my notes, so I can't show it to you now how it's look. Okay, so that's all from me. That's my last year in 1.5 hours.
Okay.
So if you have any question, please ask me. If you have any comments, I will very happy to heard anything. And I'm sorry that it was awful talk. But
Okay. All right.
thank you.
You can do this. Yeah, my hands are vanishing. No. So yeah, now it's not so easy to write on the screen with the mouse.
Yeah. It's much harder that I think. I believe that when I will show
But you,
this next year on the blackboard, it will be better.
Next year?
Yeah, after Corona
so,
crisis.
but you are in your office now, Patrik.
Oh.
Sorry.
Gone to the F-Lens and recorded it.
I know, but the microphone there is not very good. I have.
I think the new microphones came yesterday, and Vasek was working the whole day. So
In F-Lens, I just did it today. I used it today. It's perfect.
Yeah. Okay.
But I know that France is actually talking Wednesdays 2:00 in F-Lens, so we have to find another.
Okay. I think about this talk that I should it be before Blackboard, but the old microphone there was bad, and my English is so bad that it will be totally mess
Right.
of combination.
Well, before we discuss that, are there other questions about to the talk, so we could stop the recording if
Yeah, I have a question about the.
Okay.
I got a little bit lost in the ending, and I don't really remember why. So when you have this Lagrangian decomposition into the lowest order next to the leading, so why did you focus on the last one? What about the first and second?
It's because the paper which I want to generalize. So that's it.
Yeah, generalize.
They say that this Lagrangian should be Lagrangian for Newtonian gravity. And this is why I'm interested in this guy. In fact, this Lagrangian will be another Lagrangian for another non-relativistic gravity. So it could be interesting also, but I'm mainly interested in this one. It should be another theory of gravity. I don't know. I still didn't think about it a lot.
Okay. So that's interesting for the case where n is equal to 0,
yeah,
and you want to recover.
Yeah, and I hope it will be interesting for a case n is equal to 1 and n is equal to 2 also.
Okay. Yeah, thanks.
Any other question?
I have a question about the significance of sigma, because there are several possible limits of general relativity, and there are several parameters which you can take a limit of, or an asymptotic expansion.
Okay. Which one?
That's maybe a better term than a limit. So how about this sigma?
So my sigma, okay. So I define that speed of light is some dimensionful parameter over this sigma. So it's just a parameter which should, when it's go to 0, it should be the same as when the c is going to infinity. So I don't know how to answer to you.
Maybe Michael,
Change the scale of time with respect to space.
Yes,
That's
but
that's
I
significance.
also include this scale to the another guys in the metric.
And you only apply it to the gravitational part of the Lagrangian. Because such terms where sigma is appearing are also in the rest of the of the action, right?
No, I'm confused again.
There is, you just use the part which gives you the left hand part of the Einstein equations.
Yes. I don't. Yeah. I have a tensor of matter equal to 0. I don't.
But
That's
in
Okay,
principle,
thanks.
you can use it for the matter part as well, and
yeah.
in the end you get the Poisson equation for non-relativistic
Yes.
gravity.
It could be quite interesting because it has different scaling with respect to different splitting. So it could some matter cannot to couple to this to some splitting. It could be interesting.
So how is this different in the treatment given, for example, in Mr. Storm-Wheeler here? There are several chapters which there is this PPN formalism and stuff like that. So and there are several parameters, right? So this is different.
I don't know which parameters you can or how, which limits you can do in general relativity.
Oh. Okay.
Sorry.
Well, you can do a low curvature limit, for example.
Okay.
Right? Or you can do a limit like you did, low velocities.
So this should be just
limits.
This should be just low velocities limits.
Or asymptotic expansions when you want to be mathematically correct.
In my opinion, this Patrik result is important because you can get non-relativistic Lagrangian, and previous limits were restricted to equation of motions. So that's if we find Lagrangian for non-relativistic gravity, we can proceed further. We can study possibly path integral and so on. This is very important.
Yeah, I don't doubt it. My connection dropped for a bit, so I haven't heard the last part.
Mikael, are you thinking of these various expansion, post-Newtonian expansions and so on?
Yeah.
Yeah, I vaguely remember a statement that there is different kinds of post-Newtonian expansions.
Of course. It's lots of ways to do an asymptotic expansion, but I think here it is just different scale for time and space, right?
Yeah.
It would seem. All others are left alone. So
Yeah.
that's interesting. Because
That's just, let's
of
say,
course these
just naive limit, or just naively constructed non-relativistic gravity from general relativity by taking just speed of light to be infinity, nothing more. It should be still curved space and time separately, and so on.
Mhm.
Can I ask about one more thing?
Yeah.
It's related to the question I already asked in the beginning. So overall, about how I was thinking about this whole thing was that you have this sigma parameter, which you want to have. If it goes to 0, then you have the non-relativistic limit.
Mhm.
And in the end, the overall action, I thought you want it to be such that the expansion would start already at sigma to the power of 0. So is this true? Is that what you want? That the curvature terms, the minus g under the square root and the c all should work out in such a way that already the expansion starts at sigma 0, or you just want to, you could allow for terms which have negative power of sigma and then you just put them away and you focus on this
I want
Lagrangian with the bar which starts at 0.
every field I want to start with sigma 0. So I must manually get out the sigmas,
Yes.
and it's given by first by definition of the splitting of the field binds, and then that's enough, because this is metric formulation of gravity. Everything can be calculated from metric. So when you have split of the metric, everything, I can separate all sigmas just by this.
Yes, you can separate it, but in the end, in the action, you get some combination of all these fields.
Yeah.
And you could also get negative powers of the sigma in the action. But you can separate a Lagrangian which starts with sigma 0.
Yeah.
But overall, if you count everything, you can have negative powers of sigma, which intuitively would ruin the action because they would go to infinity. Is that true?
Yes. So
because if you put sigma to...
Yeah, and all fields in Lagrangians, I want also start with sigma to the power of 0.
Yes, but the action itself doesn't have to start with sigma 0, right?
Yeah. And it doesn't. It starts with some C4.
So in the end, if you would think about it, do you have some problems, or do you have to do some renormalization or something like that? Or do you just focus on the Lagrangian itself?
That's a good question. I don't know. In fact, this is something which I still need to think about it a lot.
And is it addressed in the paper?
No, they just call this guy and next leading order Lagrangian for Newtonian gravity without saying why the C's in action does not matter.
Okay. Yeah, maybe it all works out fine in such a way that there are no problems, but it's also possible.
It's
I
possible.
don't know. Okay. It's hard to see from this because there's a lot of contributions. I don't know. Yeah, but thank you for the answer.
Okay, so are everybody happy? Everybody's happy, looks happy. So next time is when?
Okay, so next time should be in 2 weeks, I think. And Klaus wants to say something to us.
Yeah.
So
Yeah,
how
I would